Welcome back to section 6.6, solving exponential and logarithmic equations. This is day 2 of our work. Let's begin. We have a property of equality for logarithms in much the same way that we did for exponentials. Keeping in mind that equations say that left and right sides of the equations are equal, in the example that they're showing here, if the log base 2 of x is equal to the log base 2 of 7, then x equals 7. If the bases are the same, we should be able to compare those other values. In example 3, we're asked to solve two log equations, and it seems like the first might be a little bit easier than the second. When we have the natural log of something equals the natural log of something else, we can just focus inside the parentheses and say that 8x plus 5 equals x minus 6. We can subtract x and subtract 5 to their respective sides, get 7x equals negative 11, and when we divide, get x equals negative 11 sevenths. We can go back and check our work. If we plug in negative 11 sevenths wherever we see x, work to find a common denominator and either add on the left or subtract on the right, we can come to the natural log of negative 53 sevenths equals the natural log of negative 53 sevenths. It seems like that is going to check out. It makes sense that the left and the right hand sides still equal one another, but keep in mind that it's not possible to take the log base e of negative 53 sevenths of any negative. E is about 2.71. What are we going to raise that value to? 2.7 to what value is going to give us a negative? It doesn't work. If we were to graph them, they basically look like the green is the left-hand side and the purple is the right. You can see that these have a sense that they're never going to intersect, so there's no solution. On the right-hand side, we have the log base 2 of 3x plus 11 on the left equals 9. If we take that and convert immediately over into 3x plus 11 equals 2 to the 9th, we can work to simplify a little bit. 2 to the 9th equals 512, and we'll subtract 11 so that we can isolate 3x. We can divide by 3 and come up with 167. If we go to check that out, plug 167 back in, we'll come up with eventually the log base 2 of 512 equals 9. You can grab a calculator, you can change your base, see if that works. You can also convert over and say that that's equivalent to saying 2 to the 9th equals 512, and you can also check that out on your calculator. In example 4, we want to solve the log equation, that is to say we want to solve for x. We have two log expressions over on the left, but notice they have the same base. We can condense those through multiplication, so we can say that that is the single log base 4 of negative x times x plus 10. We can distribute, and then if we're trying to solve for x and it's part of the log expression, then we can convert over into exponential form. So 4 to the second power equals negative x squared minus 10x, and we can simplify things by bringing the two terms on the right over to the left by adding, and 4 squared equals 16. We can factor this by saying that x plus 8 and x plus 2 multiplied together equals 0, and therefore we come to the idea that x could equal negative 8 or negative 2. When we go to check, we can plug in x equals negative 8 wherever we see x. When we simplify inside the parentheses, we come to the log base 4 of 8 plus the log base 4 of 2. If we condense that left-hand side, we'll get the log base 4 of 16 equals 2. And as an exponential that's saying 4 squared equals 16, that seems to make sense. For x equals negative 2, we plug that in wherever we see x. Again, when we simplify, we'll come to the log base 4 of 2 plus the log base 4 of 8. And that's the same thing as previously. The positions are just reversed. We'll come to the log base 4 of 16 equals 2. So in this situation, both x equals negative 8 and x equals negative 2 are good solutions. Can we do similar work with this next equation? We have two log expressions on the left They are separated by addition. We can condense through multiplication. We can distribute on the inside of the parentheses, and we can convert over from log to exponential form, so that 3x squared minus 3x is equal to 6 raised to the third power, which is 216. If we bring the 216 over to the left, I recognize that all three of those terms are divisible by 3, and when we factor that 3 out, it becomes pretty quick to see that some factors of 72 are 9 and 8, and they differ by 1, so it feels like that's going to be the way to go. And so the solutions that come out are x equals -8 and x equals 9. So once again, let's plug those in to see if they work. If x equals -8, wherever we see x, we can plug those in. And so we're looking at the log base 6 of -24 and the log base 6 of -9. Before we proceed and say, oh, it's separated by addition, we can condense that, recognize that you can't take the log base anything of some negative. It doesn't work, it's undefined. So -8 is going to turn out to be an extraneous root. What about 9? Does 9 work? If we plug in a 9, we'll be looking at the log base 6 of 27 plus the log base 6 of 8, all equaling 3. If we multiply 27 times 8, we'll get the log base 6 of 216 equals 3. And if it's easier to think of this in terms of exponentials, that's saying that 6 cubed equals 216. That's a true statement. 9 works. -8 is extraneous. Our goal in this next problem is to determine what the error is. We have two log base 4s that we're adding together. They can come together by multiplication, so that second step looks good. We can take the same base, they're choosing 4 here on both sides, and let those first terms become exponents. That's legal. The left-hand side does simplify to x plus 12 times x. Now 4 cubed is 64. We can distribute, we can bring everything to one side, we can factor, and everything looks good. So x equals -16 and x equals 4. It seems like that's okay. Alternatively, we could have just brought the two log terms together right away. We could distribute, we could convert over into exponential form, we could combine all of our terms together, and we could factor and basically come to the same information. The difference is that we're not allowed to take the log of a negative. And if we put in a -16, both of those log expressions are going to be log base 4 of something negative that's undefined. So -16 is extraneous. It does work for 4, but not for -16. 16 is okay, but we can't have the negative. Here's another practical application of Newton's law of cooling. You're driving on a hot day and your car overheats and stops running. The car overheats at 280 degrees Fahrenheit and can't be driven again until it's down to 230. It's 80 degrees outside. The cooling rate for the car is 0.0058. How long do we have to wait before we can continue driving? So let's be reminded first of all of Newton's law of cooling, and let's fill in those values and talk about them. We need the car to be cooled down to 230 degrees. Currently, it's at 280, and it's 80 degrees outside. That's multiplied times e raised to the negative rate times time, and we're going to add the 80 degrees. So we're going to become asymptotic with 80 degrees. If we left the car alone and didn't drive it for hours and hours and hours, the temperature would eventually come down to approximately 80 degrees because that's what it is outside. If the temperature outside dropped, then that would change things. So let's start to simplify things. 230 minus 80 is 150. 280 minus 80 is 200. We can divide. 150 divided by 200 simplifies to 3/4. And because we now have that equaling e to some exponent, we can convert over into log form using the natural log. And finally, we'll want to divide. It works out to being approximately 49.6. When we look back and see what is it that we were solving for, it's a little bit less than 50 minutes that we would have to wait before we could easily or safely start the car back up. Here are two examples that are a little bit more challenging. The log base 4 of x equals the log base 8 of 4x. How are we going to deal with that when our bases are different? Well, just saying that phrase should trigger something in your mind. If our bases are different, why don't we change the base? In the past, we've often gone to the common log or we've gone to the natural log. But if you notice that 4 and 8 are both multiples of 2, we could raise 2 to the second power or 2 to the third power and come to 4 and 8. Why don't we change the base on both sides, but make it a base 2? So the log base 2 of x over the log base 2 of 4 equals the log base 2 of 4x over the log base 2 of 8. Does that simplify anything? Does that help us? It doesn't help the numerators very much, but in the denominator, we can say that the log base 2 of 4 is equal to 2, and the log base 2 of 8 is equal to 3. Now, just some old-fashioned, when we deal with fractions equal fractions, we can cross multiply, and we could have 3 times the log base 2 of x equals 2 times the log base 2 of 4x. And more recently, we know that the power rule says that those coefficients of 3 and 2 can go up as exponents. So it's the log base 2 of x cubed equals the log base 2 of 4x all squared. If we simplify over on the right, 4x all squared is 16x squared. And if it's the log base 2 of x cubed equals the log base 2 of 16x squared, we can just focus on the x cubed and the 16x squared. Divide both sides of that equation by x squared, and we should come to x equals 16. Plug it back in, see if you agree. In part B, we have 2 to the 2x minus 12 to the times 2 raised to the x plus 32 equals 0. This is a trinomial, and we have factored trinomials in the past. This seems a little bit more challenging. If we observe for a moment and try to look at some similarities to things we've done in the past, the 32 is a constant, and then when we work from right to left, the second term has 2 to the x, and then the third term, far left, has 2 to the x squared. So we can make a substitution, whatever variable you want. But if we say, let's allow w to equal 2 to the x, then that would switch over to w squared minus 12w plus 32 equals 0. That looks much more manageable. We can try to factor that, and that can lead us into realizing that w could equal 4 or 8. Remember that w equaled 2 to the x, so we have to substitute back in and say that 4 is equal to 2 to the x, or 8 is equal to 2 to the x. And if we know that 4 is 2 squared and 8 is 2 cubed, we can replace those x's, which allows us to finally say that x has to equal either 2 or 3 in order for this equation to work. Thank you for watching. Please continue to reach out to ask questions if you have them. Your homework will be posted. Have a great day.